Welcome. In this session, we will continue with the Compuplast Virtual Extrusion Laboratory 2D FEM module and create a project for the die lips geometry that we created by importing a DXF file. So we go to the Project tab, create new, rename, and click Edit. And as you can see, the module has found the geometry that we entered, and it's determined that it is an axisymmetric domain based on the orientation, that being the flow going upwards and the axis of symmetry being the y-axis. So here we're going to just select the material, and we'll go to our LDPE here, which is already in our database from our last project. And we'll leave the iterations again as normal and click Save and Solve. Now the solution time is a little bit longer because of the number of elements that we used in this simulation, but it's still relatively fast. Okay, so here is the project, the results, and again we can revolve the view and zoom out and switch this to 270, and we get our cross section of our flow field. And the results that we're looking at are the velocity variable, and velocity of course is blue on the walls, which is 0, and maximum in the center of the flow field, which looks to be about 1.38 millimeters or inches per second. So again, we can go back now to our cross section and we can look at other variables. For example, we can go to pressure, and here is our pressure drop in this geometry. It looks to be about 494 psi. And we can also look at variables along a surface by clicking this icon up here and selecting a surface. Let's select this surface here, and we see our pressure drop, a relatively steeper pressure drop here where the gap is small, then a more gradual pressure drop in the large gap region, and then a much higher pressure drop in the small gap region near the exit. Now on this surface we can also look at the shear stress, and we can see that the shear stress is relatively high where the gap is small, and then drops where the gap increases down to a value of about 4.3, and then gradually increases as that channel gap is getting smaller, and then increases up again to the shear stress in the die lips of about 11 psi. So that looks relatively good. Now let's take a look at a result on a cut. So we'll come here, we'll do a cut, and here we show the shear stress. Of course, the shear stress is relatively should be relatively symmetric, but it is not. And this is a result of the irregular mesh that's used, the triangles. Because the mesh density isn't uniform, we start to get somewhat irregular results. If we look at the velocity magnitude is not too bad, but again you see it's slightly skewed because the elements aren't even. Now one way to kind of correct for this in the small gap regions is to put a structured mesh in that region. I'll show you how to do that. We'll close this. We'll edit the project, and within the project we'll select the geometry and we'll edit the geometry. So here's our geometry here, and to add an element in the end, what we're going to do is we need 4 nodes, if you recall, to create a super element, and we can add a node onto an edge by using the node modify edge command, add on edge. So we can you can see as I move my mouse along the edge, a node is appearing. And basically you can just eyeball a position across from that node and click, and now a node is added. If you right click to release the command, we'll see the node is added, and then we can simply go to the element, add quick option, go near this region, you see the 4 nodes are highlighted, and then we go to the edge, right click once, and then go to the edge divisions, and perhaps go to 6 divisions. And now when we create our mesh and we click OK, we see that this mesh here is more structured, and then we have the random mesh prior to this section. So we have now a hybrid mesh, which is okay. You can file, exit, yes, save it. And now again we do a save and solve. So it's always best to use a structured mesh in small gap regions to ensure that you get at least a minimum number of 4 or 5 elements across the gap. So now the results have opened here. So here's the results. We can see that the velocity is slightly different, not too much. We'll check also the pressure drop. And the pressure drop has slightly reduced, 400, I think it was 494, now it's 483, so 10 psi, but not very significantly. And when we go to do a cut now here at the exit, we see that the pressure is completely even. That's the variable on the main grid. That's what shows first. But if we look now at velocity, we see that the velocity profile is much, much more symmetric. And in fact, even if we add the stress on this graph, we see again that the stress is much more symmetric in this geometry. That's still a little bit, it should be a straight line, still a bit of fluctuation. Perhaps if we had a few more elements across that gap, this would be a little bit smoother. But that's how we import a DXF file and create a mesh, and generally recommend a hybrid mesh with a structured mesh in the small gap regions, perhaps even on the inlets. We should have a structured mesh, and then a random mesh in the larger areas. Okay, well that's it for the 2DFEM module for now. As I mentioned, it can be used for a variety of different flow fields and anywhere where you have an axisymmetric or even planar flow field. Thank you very much.